Okay, class, for our next lesson, the 1.1 overview of statistics, you'll notice that this one is not a review lesson. This one is actually in the textbook. I'll zoom out a little bit for you. Okay. And what I've done in this document is make some notes that match up pretty closely with what's in the textbook. You can load the e-text in MyMathLab to read what the publisher has written. And if you want to read my note file, I've also added it in MyMathLab. The way that you'll find it is you can go to the course tools in MyMathLab in the left column, and then that should open up a submenu, and one of the choices should be document sharing. If you open up that link, document sharing, you'll see a link of all the files that I'll upload there in the course. These are the ones that I like to teach from and make my notes from. Okay, so the first chapter in statistics, the lessons that we'll cover, really don't have any calculations involved with them. So in that sense, it'll look a little differently than, say, most of the math classes you've looked at so far. We just want to introduce some of the terms we'll use, talk about some of the vocabulary we'll use for this course, and then we'll build upon that later. I promise there'll be some good calculations to come from this later on. Okay, so that's our goal as an introduction, and just to become more familiar with the vocabulary that we use in this course. One of the main vocabulary terms that we will use is data, or data, you pronounce that either way, which is simply information, just a word that we use to talk about information that we get somehow by either observing something, counting something, measuring something, or written responses to a question. We could ask someone a question, and we'll get into those processes a little later. Okay, but data is just information, just some kind of information that we can do something with. Statistics is going to be the science of collecting, organizing, analyzing, and interpreting that data. Okay, so once we have the data, what do we do with it? That's the statistics part, where we do something with it. Okay, two types of data sets that we'll talk about are population and a sample. We use the word population to talk about all the outcomes that are of interest. So for instance, if we talk about the United States population, we're talking about every person that lives in the United States. A sample would be some subset of that population. So if we take all the people that live in Texas, that would be a sample for all the people that live in the United States, which would be our population. However, if we define our population a little differently, let's suppose that we define our population to be all the people that live in Texas, then a sample for all the people that live in Texas might be all the people that live in Athens, Texas. That would be a subset of our population. So the population will depend on how you define it. Notice that all the people that live in the United States would be a subset for all the people that live in the world. So in that case, if our population is all the people that live in the world, then the people that live in the United States is no longer a population. That would be the sample. So pay careful attention to how those are defined, and then you'll be able to tell whether you have a population or a sample. We use population when we're talking about everything that could happen, and we use sample when we're talking about some part of that, some smaller part. Now, as far as data goes, we can have data that's qualitative or quantitative. That will actually be the subject of our next talk. But we use the terms parameter when we're measuring something about the population, and we use the term statistic when we're measuring something about a sample. Okay. So for instance, using the population as being all the people in the United States, and a sample being all the people in Texas, we might be able to measure something there. We might be able to say something like the average age of everyone that lives in the United States is 45.2 years old. Now, I don't know if that's true or not. I just made that up off the top of my head. But if that were true, then that would be a parameter. That would be a way we could measure the population. We could measure the average age. If we measured the average age of everyone that lives in Texas and we get 45.1 years old, then that would be a statistic. That's some measurement of our sample. Okay. Now, for an example, let's go through a few examples here based on the 2015 NFL season. We have 32 teams in the NFL. Each of them plays 16 games, and that makes the entire season. So based on that, let's determine whether each set is a parameter or a statistic. Now again, before we answer these questions, we need to understand what our population is. What is the set of every outcome that's interesting? So the way I've defined this, the 2015 NFL season, we have 32 teams that play 16 total games. So our population would be all of the games that were played in that season by all the teams. Okay. Not anything that happened in 2016 or anything that happened in 1998, but all the things that happened in 2015 relative to all the games that were played that season. Okay. That's our population. So if we are given that the Dallas Cowboys won 4 games and lost 12, it's easy to see that that measurement is not something that's measuring the entire population. We're not measuring something about all 32 teams. We are measuring something about all 16 games, right? 4 games and won and 12 games lost is 16 games, but that's 16 games for only one of the teams, not 16 games for all 32 teams. So therefore, this set is a sample, and anytime we measure something about a sample, we have a statistic. Okay, so the Dallas Cowboys won 4 games and lost 12 would be a statistic. Okay. Next example, 80 players have taken at least 1 snap as a quarterback and thrown at least 1 pass. And of those, 12 have thrown for more than 4,000 total yards. Okay, now we haven't said anything about all the teams, but we can infer that this is talking about all the teams, all the games, all the seasons. We're given 80 players have taken at least 1 snap as a quarterback, and we can infer that that's information about every single team in the league. So since we're measuring something about every team in the league, specifically we're measuring how many have thrown for 4,000 yards or more, then our set in this example is a population. We're discussing something about all 32 of the teams. And anytime we're measuring something about a population, we say our measurement is a parameter. And notice how the alliteration combines nicely here. We have sample with statistic, S with S, and we have population with parameter, P with P. So that's an easy way to remember those terms, that a statistic always measures the sample and a parameter always measures the population. Okay, next example, Darren McFadden has the most rushing yards of any Dallas Cowboys player. Well, since we're measuring something about only the Dallas Cowboys, that's only one team, this is clearly a statistic, just like our first example. Okay. We don't have any information about the other teams, so only a statistic. J.J. Watt has 17.5 sacks this year, which is the highest of any player that plays in the AFC South. And for those of you who are not football fans, the AFC South has 4 teams. So when we're talking about the AFC South, we're talking about 4 teams. Well, four teams is not all 32 teams, right? Not measured something about the entire season. So again, for that reason, this would be a statistic. Okay, we're not measuring the entire population. We're only measuring a sample. Now, J.J. Watt has 17.5 sacks, regardless of which teams we're measuring. I mean, he's one player. He has a certain number of sacks that year. But the second clause, when I state that that's the most in the NFL, Now I'm making a statement about all the games played and about all the teams. His sacks were the highest in the entire league, in the entire season. So I've measured something about the entire season. I've measured all the players who have sacks, and then J.J. Watt was the highest of all those players. So even though the information is the same, notice 17.5 sacks in both cases. In the first case, since that was a measurement of only 4 teams, it would be a statistic. In the second case, we're measuring something about every team. Even though the measurement's the same, this is now a parameter. So again, whether we have a statistic or a parameter is going to depend a lot on how we define our population. Next one, 13 teams won more games than they lost. We can infer there that we're measuring something about all the games played. So this would be a parameter. Let's just do P for parameter. And then the last one, Carolina Panthers won the most games that year. Well, how do I say who won the most games if I have not measured the wins for every single team, right? By saying that they won 15 games, which was the most of any team, that implies that I've measured how many wins each team had that year. And as a result, this has to be a parameter. Okay. Hopefully that idea kind of makes sense. Those can be a little confusing. Just think about them real carefully. Think about what's our population, and then are you measuring that entire population, or are you measuring some part of it? Okay. As far as types of statistics go, our book references 2 types: a descriptive type, which means what you think it should mean. It means a way to describe things. So if I collect some data and I make a chart for you and summarize some things and display, communicate what the data says, then that's in the realm of descriptive statistics. If I go a little bit farther with the information, if I use it to draw some conclusions, make some inferences, make some predictions, then I'm in the realm of inferential statistics. Now, to say much about inferential statistics requires a background of probability. So if you've looked ahead as to what we're going to study in this course, we introduce in the first 2 chapters the ideas of what statistics are, what data is, and we'll go into some descriptive statistics. Well, then to go much further, we have to take a break and study probability. So the course will be set up as descriptive statistics first, then some probability. We'll actually spend quite a bit of time on probability. And then after that, we can get into some inferential statistics. And then by that time, the course will be over. And if you happen to like what you're studying, you can study some more statistics and get into that quite a bit. This is sort of the main area that real statisticians and actuaries kind of make their living in. For instance, if we study how many car crashes or how much money it costs to fix vehicles for a particular age group, say young men who are 16 to 21 years of age, if I were to make a chart that shows those things to someone, I would have used descriptive statistics to kind of display that information. If I further do some calculations and come up with a conclusion that says that males ages 16 to 21 are much more likely to be in car accidents, and they cause on average 4 times as much damage as, say, adult women 45 to 60, then the insurance company can use that information. They can draw some conclusions on that, and the result is probably the 16 to 21-year-old males will be charged more for their insurance than the 45 to 60-year-old females. Just an example about how those ideas are used in real life. If you've ever wondered why one person pays a different amount of insurance than another person, and why different model vehicles require different amounts of insurance, that's why, because the more you have to pay for insurance, the more likely that either that vehicle will cost more to repair, or that age group is more likely to be in an accident. So Is that fair? Well, that's a completely different question, because surely out there are some 16 to 21-year-old males who are probably much safer drivers than some 45 to 60-year-old females are. But in general, that's been discovered to not be the case. That age group in particular is a very high risk age group for automobiles. Okay. Next lesson, let's continue with 1.2, which is about data classification. Again, this same file I've uploaded in my MATLAB. If you can't see this one real well, you can follow along from there. We mentioned earlier types of data being qualitative or quantitative. Let's talk about that now. Qualitative means that it has some quality associated with it, which would be some attribute, some label, or some non-numerical information. Quantitative means that we have some numerical measurements or counts. There's some numbers involved, and not only numbers, but numbers that I can do some calculations with that make sense. Think quantity. Quantity is an amount you have to count. You have to use a number to determine a quantity. Whereas a quality, like how happy we are, we don't need any numbers to measure that. Okay. So that brings us to 4 different levels of measurement that are important: nominal, ordinal, interval, and ratio. And I like to think of the kind of simpler words here, or root words. When we're talking about nominal, kind of the root word there is name. Nominal is a fancy way to say name. So if we have data at the nominal level, what that means is I can give it a name, and that's it. I can't do any calculations that are meaningful. Okay. Ordinal means that I can put the data in order. I can somehow, there's an order that makes sense from smallest to largest. And interval, this one will be less obvious. Interval is a fancy way to talk about subtractions or differences. And if I have data at the interval level, that means I can order it and I can calculate some differences. Now, the book goes into a kind of detailed discussion about what an inherent zero is. That's sort of an important idea. I tried to give an example here about an inherent zero or a non-inherent zero. An inherent zero means that zero is actually measuring something. So an example would be, say, weights. If we're measuring weights of people, then a 200-pound person, a 100-pound person, 300-pound person, those all make sense as being some number. And if you look at zero, zero makes sense there too, right? Because what does 0 pounds mean? It means no weight at all. There's a zero there that makes sense. And negatives don't make sense on this scale. You can't find a person who weighs a negative number of pounds. So in that sense, weights have an inherent zero. They have a zero that means something, that doesn't represent only a position. Now, an example of a scale where you see zero, but the zero is not inherent, would be the classic temperature scales of Fahrenheit and Celsius. Now, on both of those scales, you can get a negative temperature. For instance, in Fahrenheit, the temperature -32 is pretty important. That's the, I'm sorry, mess that up. 32 is a positive number, but that's the temperature that water freezes on the Fahrenheit scale. And 0 is cold. That's colder than what water freezes at. But if we go below 0, for instance, we could have like -10 Fahrenheit, -20 Fahrenheit. Those kind of temperatures we don't see very often in this part of the world, but in Canada or Alaska or northern Russia, we would see those kind of temperatures. And that makes you think, what does 0 mean on that scale? Not really anything, right? 0 is not a measurement of nothing on that scale, because 0 is just some placeholder for that temperature. Similarly, on the Celsius scale, 0 at Celsius is the temperature that water freezes at. Well, we can easily get below 0 on that scale too. We can measure negatives on the Celsius scale as easy as we can on the Fahrenheit scale. There's another scale you may be familiar with from your science courses called the Kelvin scale. That scale actually does have an inherent zero, a zero that makes sense. Not many people talk about Kelvin in everyday life, but if you're curious there about making a temperature scale where 0 meant nothing, that's one of the scales that you could use to do it, the Kelvin scale. If we're at the ratio level, that means that we do have an inherent 0, and that means that our divisions make sense. So for ratio, think divide. Can I divide and have them make sense? Okay, so let's do some examples. We'll talk about each level of measurement, and you might notice that if we go in order here, if I can divide two numbers, let's go this way. If I'm at the ratio level and divisions make sense, then surely I can subtract the numbers, right? Subtractions would make sense. If I can divide numbers, I can subtract numbers. And then to continue, if I can subtract numbers and they make sense, then I certainly could put them in order, right? If I'm able to subtract them and it makes sense, I can certainly order them. And if I can order them, if I can put them in order, I certainly could give them a name. So the ratio level, we call that the highest level. And if we're at the highest level, then we're at the other levels too, okay? If we're at the interval level, then we're at the ordinal and nominal level as well. If we're at the ordinal level, we're also at the nominal level. So if we're at some level, we're at all the levels below it included. So for that reason, we normally just give the highest level of measurement. What's the highest level we could achieve for each data set? And then it's implied that we could measure below that. Okay, and then also let's state quantitative or qualitative. So first example, basketball players play a position of guard, forward, or center. So clearly guard, forward, and center, there's no way we can count or measure those. So this is qualitative data. Okay, there are no numbers associated with the data. And if that's the case, then I can't divide, I can't subtract, right? I don't have numbers to deal with, so I know I'm not in one of these two levels. But I might be able to put things in order even though I don't have numbers, and I certainly could name them. So let's see, the real question becomes, can I put them in order? Because if I can't, then I'm at the nominal level. Okay, so guard, forward, center, is there an order that makes sense to those? And the answer is not really. You might say smaller players usually play guard and bigger players usually play center, but I really can't put these in any kind of order. So we have to conclude that this data set is only nominal. The best I can do is give these names. Okay, next one. A new book can be purchased as hardcover, paperback, or digital download. Well, that's very similar to the basketball positions. I can't measure those in any way, and I can't put them in order. So we have the same solution there, qualitative and nominal, just ditto, same as above. Okay. Now movie ratings are always G, PG, PG-13, or R. Again, G, PG, PG-13, R, no numbers associated there. Even though the 13 has a number in it, it's really just a label. There's not really any calculation I can do with that number. And then I don't have numbers for the others anyway. So this is also qualitative. Let me just do QUAL for qualitative. And then the second question, what's the highest level of measurement that I can have for this data set? Well, if I'm at the qualitative level, I certainly can't do subtractions or divisions, so these two are out. But qualitative data sometimes can be put in order. And that's what we have here. The movie system ratings, G, PG, PG-13, and R, those have a natural order to them about what sort of ages it would be appropriate to watch those movies for. And then the numbers for what age would be appropriate, of course, depends on the parents and what age they would allow their children to watch a certain type of movie. That's going to vary from parent to parent. But in any case, there still is an order implied here. G, of course, is less bad than PG, which is less bad than PG-13, and less bad than R, et cetera. So these are qualitative data, and at the ordinal level of measurement. There's an order that makes sense here. Okay. Now, the next example can be tricky, can be confusing. If we have players on a football team given jersey numbers. Now, jersey numbers, at first glance, you say, numbers are quantitative. But in this case, they're not. Here, even though we have numbers on a jersey, those numbers I can't really do any calculations with. I can't add any numbers together and have it make sense. I can't subtract them and have them make sense, because the jersey numbers, even though they're numbers, they're not measuring anything. You know, who's wearing number 99? Who's wearing number 2? Who's wearing number 5? What do I get if I take any of those numbers and add or multiply or subtract them with each other? I don't get anything that means anything. So in that case, the jersey numbers are not holding any important information. They're just holding a symbol to represent that player. The same way that, say, I could label them. I wouldn't have to use numbers. I could use any symbol I wanted. I could have the jerseys be letters instead of numbers, and I would get the same thing. I would have a label there on it. So even though the jersey numbers are numbers, they're not numbers that I can do any meaningful math with. So they're qualitative. Okay, qualitative there. Important you understand that one about jersey numbers being qualitative. And then further, you might argue that you could put these in order for a football team. Like traditionally, if you study football some, the offensive line usually wear numbers in the 60s and 70s. The quarterbacks usually something between 1 and 19. And the wide receivers are usually in the 80s. But if we kind of extend that to a basketball team where the jerseys don't really mean anything, they're just random numbers. And in general, the numbers don't really mean anything here. They're just labels. Then we can see that you can't really put these in an order that makes sense. Okay, you could label them 1 to 99, but what does that do? Does that separate you by position or something? Probably not. So let's go with nominal here, that these are just names. Okay, all students enrolled at Elkhart High School are in grades 9, 10, 11, or 12. Actually, let me back up before we do that. One more note on the jersey numbers. Similar numbers that you can't really do any mathematical calculations with, where you would reach the same conclusion, would be telephone numbers. Right? Think about telephone numbers. What do you get if you take your telephone number and subtract someone else's telephone number? You don't get anything meaningful. So in that case, the numbers are just labels for something. Postal zip codes are the same way. And you could probably think of some other examples there. Social Security numbers are similar, although I think the Social Security numbers sort of do have an order to them. So that might be ordinal for those. But back to the high school students being in grades 9, 10, 11, or 12. Okay. So can I do some meaningful calculations with these? Yes, I can this time. Take, say, 12 minus 11. Does that give us anything useful? I think I'm frozen here. Let's see.